My name is Dmitry Muktasimov, and I'm learning machine learning. I'm using Feynman technique to improve my learning process, but explaining to myself is not much fun. That's why I'm recording this video. Today I want to show you how a derivative of a function can be used to find a local minimum of a function. This is a kind of prerequisite of understanding how the gradient descent works, because derivative is related to gradient calculation is actually very much similar to a gradient of in one-dimensional space. But we are not going to review vector calculations now. We just use derivative. So imagine you have Cartesian coordinates and with x and y axes, and we have a function, a parabolic function here defined, f of x, which is equal to x squared minus 6x plus 10. So we already know the function, but our goal is to use an algorithm to find its minimum value, a point of its minimum value. Well, here's the origin, and when we just look at the function graph, we actually can scan with our eyes, and figure out that this is a local minimum. But how can we do it with computers? Of course, there is an algebraic way to find local minima when you calculate the determinant of the function and do all this stuff, but that's not what we're interested in, because when there are more than one variable in a function and the computer algorithm is involved, it's better to and easier and probably the only way possible to find a local minimum of a function in multi-dimensional space, to use a gradient descent algorithm. And here what we can do, so first of all, we can actually pick any random point on a function graph, and start from that, approach step by step to find the local minimum of a function. So there is a good explanation, like intuitive explanation of gradient descent in Wikipedia. So imagine if you close your eyes and you are walking on some curved ground surface, and you need to just get to the lowest point. So basically you try to step down, tries to step up, and figure out which way is descending direction, and you just step by step go descend to that. So here we also need to do the same thing, but we need to do it in some formal way that we could be programmed in some programming language. So one thing we can do, we actually can calculate derivative of a function in a certain point to figure out what's the function behavior in that point. Does it increase or decrease with increase of its variable? So if you remember your high school, then the derivative of a function at a certain point is equal to the slope of a tangent line at that point. And actually, by definition, a derivative of a function actually gives us how fast the function value changes with respect to the change of its variable. So this can be used to to find the lowest point of a function. It's actually local minima, because if you have a different function, like if it has multiple local minimums, this algorithm, the gradient descent algorithm, or the algorithm that I'm currently describing using just derivative, it will find a local minimum. All right, so how can we use it? Because the derivative of a function defines how fast the function and what direction it changes. We can actually use this information to figure out how we need to change the value of the function variable to change the value of the function. And what we can do, we actually, if you say that this point is 0 and this point is an, the point where we actually have local minima, we can say that ai plus x is equal to ai minus s. We will call it a learning step, times derivative of a function at point ai. So we can apply this formula iteratively to get to this point a n. And at this point, we have a local minimum of a function. So let's say we have a0 is like equal to 1. And we are trying to apply this step-by-step algorithm where we can approach to the actual an value. One thing we should do first, we actually need to figure out what's the function derivative is. And the derivative of this function is 2x minus 6. All right, let's take a learning step of, let's say, 0.001. All right, so we want to calculate a1, which is equal a0, which is equal to 1, minus learning step 0.001 times derivative of a function, and derivative of a function is 2x minus 6. And we substitute 1 for x, which is also a, okay, I'll write it down like a0 minus 6, like this, and a0 is equal to 1. And now we're going to calculate a1. So a1 is equal 1 minus 0.001 times 2 minus 6 minus 4, and this equals to 1.004. All right, so what it says that we have to move our point to 0.4 units, like here, and this is completely in line with our intuition, right? So because we need to move to the right to actually achieve the local minimum. And here we have another tangent line, which slightly different, has slightly different slope. Here I should say that we actually took 2 small learning steps, and let's redefine our learning step. Let it be 0.1. I mean, I think we're going to get there faster. So A2 equals to A1, which is equal 1.004 minus 0.1 times 2A1 minus 6. This is equals 1, 0.4, and equals, so we can, I'll make some calculations quickly. So okay, and then it equals 1.4032. All right, so we advance it a little bit here, and so on. We are going to move somewhere here, and then if learning at some point we actually go into, we can move like the other side of the local minima. In that case, the slope is going to become positive here. And let's say, so the local minimum here is 3. I know it's because the local minimum is where the derivative is equal to 0. So let's say that we somehow stepped too much, like for example for A10, which is equal A9 minus 0.1 to A9 minus 6. So let's say A9 is 3.5, and here's the 3.5. And then what is going to, what the value of A, what's going to be the value of the A sub 10? Well, let's calculate it. So it's going to be equal 3.4. So you see, now we are moving like to the opposite direction. So it was 3.5, and now it's 3.4. So this is how, using derivative, you can actually slowly move from further point from the local minima to the closer point of the local minima. And even if you jump through that point, over that point, you are going to get back by the algorithm, because if you jump over it, it will get you back to this point. And the question is, how are we going to stop? When we going to stop? Because a computer calculation is actually can happen that you are going to jump around this point infinitively, because you never can be exactly at the point of the lowest value. So what we should do, we should actually define the error value that we are good enough. Basically, meaning that how close to the local minima is good enough for us. And to do this, we can actually use the derivative. So we know that the derivative at some point is equal to the slope of the line, and it's equal to 0 at local minimum of the function. So we can say that if a derivative at certain point an is less or equal 0.1, let's say, then it's good enough for us. Actually, absolute value of the derivative. Thank you for watching. If you have questions or comments, write them down below.